We can go? Okay, fine. All right. So, good evening and welcome to the 12th week interaction session. This is probably the last interaction session that we're going to have. So, and this is the last week of the course. And to quickly brief you about the contents, we talked about networks. So we were talking about the components that were required for optical networking last time. Now we talked about some network architecture. So I gave you an introduction of why you need this idea of networking, a structured way for networking in optical networks. So basically, we talked about some introduction to why we need a classification, etc. And then we talked about the layers of optical networks. After that, we talked a little more details of layering. So the basic architecture of the networking in a communication network has to remain the same. The optical element has to just slide in without disturbing the basic architecture. So we talked then about SDH or SONET layering framing. Then we talked about the network topologies. This was more of a physical layer topologies. We talked about the bus, the ring, the star and access network, essentially what are called as passive optical networks. And these are the networks which are servicing to the home for us. These access networks, short distance network, also include the data center networks and also the optical interconnects. And then I gave you an introduction of why this short distance networks are becoming very relevant in case of front hauling in the wireless communication scenario. So these were the topics that we discussed. Now, as usual, we will go on to discuss the assignment. There were some questions I have answered in the assignment window itself. In the forum window. If there is anything else, you can directly type in right away. If not, as usual, we will move on to this assignment solutions. So the first assignment question is, let's just pick the questions now. Yeah. So the first couple of questions were based on passive optical network architecture. As usual, I will not give you the exact solution, but I'll tell you how to do this solution. So from a metro access network, you have these stations which are called as optical line terminals. And then there is a extended reach PON. So there is a fiber. And then there is a 1/n splitter. And these splitters are serving what are called as ONUs. So this is ONU 1. Similarly, you have ONU 2. And in this particular network shown, you could end up having ONU N, right? So there are N ONUs. In the downstream, we know that all these, the way that it works is this is all in the TDM architecture is what is shown here. So the packets that are meant for each ONUs are aligned in time, and and they are split to in the downstream. In the upstream, each ONU will send its own packet, and there is some intelligence in the OLT which will basically range the each of these ONUs. So it's not necessary that in reality these ONUs are kept at identical distances. So there is always a ranging that happens, which basically tells what is the distance between the ONU and the specific ONUs to OLT. So the downstream is fairly straightforward. You are in a kind of a multicasting mode where all this data is available to all the ONUs. Each ONU knows the timing at which it has to look for its own information that is meant for that specific ONU. Whereas in the upstream, what happens is these ONUs will keep sending this information at random times. There is some intelligence, some timing in architecture that needs to be built in the OLT box, which identifies the frames that are coming from specific ONUs and arranges them back in the same frame structure. And that's how communication happens. Now, we have talked about this in the class. Now, the question here is, first question is, what is the maximum optical loss for n is equal to 64? Now, n equal to 64 is really a large split ratio at the two wavelengths. So what is the information given? There are two possible wavelengths. 1490 is for downstream. So for downstream transmission, we are using 1490 nanometer. And we are for the upstream traffic, we are using 1310 nanometer. And this is just ease of operation, simply because you can, if you use two different colors, you can filter out the information correspondingly. We also know that the length, fiber length between OLU, it is not OLU, it's actually OLT. OLT to star coupler is 10 kilometers. So this is 10 kilometer. And the maximum length from the star coupler to ONU is 5 kilometers. So let's work with the maximum length. So the total fiber length is given. Because whenever you do a link budget, you look for the maximum length of the fiber. Now, consider only the intrinsic splitting loss of the 1/n coupler. We know that there's something called as excess loss, which is coming in because of the imperfection in the manufacturing of the coupler. So what we are saying in the question is that consider that imperfection, ignore that imperfection. In the last question in this assignment, we have considered a problem where we are considering that imperfection. So, so the question is, what is the first question is, what is the maximum loss at these two wavelengths? Now, why are the losses different for wavelengths? That's primarily because, the splitter, we assume that it is not, the information is not given. So we assume that the splitter works equally well for both 1490 and 1490 and 1310 nanometer. But the fiber loss is in 1490 case, the fiber loss is 0.3 dB per kilometer. Whereas if you're using 1310 nanometer, the fiber loss is 0.5 dB per kilometer. And you're using 15 kilometer of fiber. So this difference in loss will build up to a significant difference between the upstream and the downstream. So the problem is very simple now. So you've identified the reason for the difference in losses in upstream and downstream. So now you calculate the fiber loss plus, so the total loss is fiber loss plus the splitting loss. And fiber loss is different for the two wavelengths. So in one case, it is 1490 into 0.3. In another case, it is 1310 into in one case, it is 15 kilometer into 0.3 dB per kilometer. In the second case, it is 15 kilometer times 0.5 kilometer. So you can calculate it differently. Split loss, as I said, it is identical. So, and we have seen in the star coupler, when we did discuss star coupler, we discussed the design, and we said that the split loss for the loss for the star coupler is, if it is a 1/2 coupler, the loss is 3 dB because you have, two output ports. 1/n coupler, the star coupler split loss is very easily can be calculated as 10 log 1/n. So for n equal to 2, it is log of half, so it is minus. So I'll put a negative here so that, because we are already indicating it is loss. So either write it this way or you can write it as 10 log of n, doesn't matter. That is the loss. So essentially, we need to remember that this is the loss. So if it is a 64 split ratio, you can calculate the loss. Add it with the respective loss, you will get the upstream loss and the downstream loss. So that is for the two wavelengths. Now, the next one is, next question is, I hope that is clear. When you say respectively, it means just the two wavelength numbers. I mean this. Actually, the numbers are such that the first case is the first answer is for 1490 nanometer, and the second answer is meant for 1310 nanometer. But then you can pick. There is only one choice in that which actually gives the correct answers for both 1410 and 1490 and 1310 nanometers. So I don't think it's going to be difficult for you to identify which one is 1490 and which one is 1310 nanometer. Any questions on this? Okay, I don't see anything in the chat window, so I will go on. So in the second question, what is given is what is asked is for a direct detection receiver limited by thermal noise. So that not the sensitivity is not dependent on the power, because the power falling upstream and downstream, the power budget could be different in the upstream and downstream, because you can very clearly imagine the OA smaller power, it receives much larger power because it is basically getting the power from the ONUs. The question is, receiver sensitivity is related. Assume that the transmitters at when you have the same optical, and so which means the receiver sensitivity is the same, the transmitter is the same. Where did I hear? Okay, so the question is the downstream and upstream channel. So you have to think here, if the receiver is the same and if it is the thermal noise that is affecting the system, the maximum and assume that there's no multicasting, which means there's no single time packet that is shared among different ONUs, right? I mean, all these ONUs basically get different time packets, since that they are basically getting one ONU2 is sharing this, and so there is a difference. Then you look at what is the bandwidth for the downstream and bandwidth for the upstream. Right? I keep hearing this ding sound. Why? Yeah, probably nothing's happening. So anyway, so the bandwidth for the downstream, is that the bandwidth of the is different from the bandwidth for the upstream, because in the upstream you have only the receiver in each one what is being transmitted. Right? If the, let's say, upstream data or several n bandwidths, Mahesh, can you confirm if you can hear my voice? Hello? Can you type in the chat window if my voice is audible? Hello? I can see now. Can you confirm you're able to see my whiteboard and hear me? Can you check again now? But it says presentation, you are presenting your screen. Okay, let me just try it with a different browser now. and hear me? Can you check again now? But it says presentation, you are presenting your screen. Okay, let me just try it with a different browser now. Is it okay now? Okay, fine. Okay, so this is even more compelling reason why we need our optical communication network to be much more stable and much more reliable. Um, so I hope you heard this story that what I talked about in terms of bandwidth in the downstream and upstream. So the upstream data rate can be potentially n times the downstream data rate, but we typically don't use that. Okay, so now we move on to the third question. The third question says three SONET systems are available: STS 3, STS 48, and STS 192. Now, we discussed in class in detail what this terminology means. STS3 came with STS3 is actually 155.52 Mbps. You have to go back. Now, these are numbers you don't have to mug up, but you from the lookup table you can generally figure out. STS48 is 2.5 gigabits standard, so which is 2488.32 Mbps, which is actually around 2.5 gigabits per second. STS 192 is our 100 gigabits per second standard, which is actually at 10 gigabits per second standard, 9953.28 Mbps. Right? So this is what we are calling as roughly 10 Mbps. So this is what we call as roughly 10 Mbps, 10 Gbps, 2.5 Gbps, and this is 155 Mbps. These are the most commonly used standards. Question is, how many voice channels can be calculated? Now, this is very, very easy. Now, you have this much as the capacity. How many voice channels of 64 kbps can be calculated? This is trivial to kind of find out. The ratio, you divide it by 64 kbps to find out what is the voice channel. So, I mean, this is not really challenging you at all. The reason why I put this is because to kind of, for you to take home the point that these are the three most commonly used data rates, and the corresponding standards are 348 and 192. The next question is also trivial. We are now moving from voice channel to video channels. So from 64 kbps, we move to 20 mbps. In our very, very first lecture, or in the first week, we learned why the voice channel requires 64 kbps. How did that number come about? So you can now correlate with that and say that if I were to transmit a voice channel, or in the case of a video channel, how many can be transported in each of these cases. So depending on how many video channels you want to transmit, you can now kind of think of designing the system to deliver those many voice channels and video channels. For instance, if you look at an architecture, if you look at an architecture like this, for instance, and you want ONU1 is a home now. Now, this is how you can do your network planning. Now, you can say that each, let's say you're kind of installing this passive optical network in a domestic kind of apartment complex kind of scenario, and let's say that you want to provide, let's say there are 3 different rooms inside the home, and there are 3 different connections, or 3 people are downloading at the same time. So how many video channels you want to download at the same time? You would say, okay, I want to download, let's assign 1 video channel per device, or per, so I mean, you could think of, let's say, you can plan it that way. You can say that, okay, let me service 3 channels. So which means that you would require 3 video channels, would mean that it would require something like 60 Mbps. Now, 60 Mbps to service 60 Mbps in each of these ONUs. What should be the the STS standard that you want to now design your equipment for? And if this is 60 Mbps, and then let's say there are 64 channels, so the total number of channels is 60 into the bandwidth requirement is 60 into 64 Mbps, right? So this is your bandwidth with which your OLT has to service, and for the OLT to service that bandwidth, now you can calculate what is the framing standard that you need to choose. So this is to make you think about how to now design the complete network. Okay, so we move on to the next question. I hope this is all fine now, or we are seamless connection. So the next question is about a grid. So there were a couple of questions by somebody in the forum about this next question. I would request that, don't mug up any formulae. I would request that you try to solve it for this particular problem in context. So I'll tell you how to go about doing this. So there's an M by N rectangular grid of computer stations are shown in the figure, where the spacing between the stations is D. So we have let's say M stations along the length, and let's say there are N stations uh, along the so M columns and N rows. Now these are points. The points are computer stations, and the spacing between is D. So I mean, I shouldn't be drawing this way. It's all equispaced, right? So I should make sure that the spacing is identical. But anyway, there are N rows. What is given to you is this spacing is D. This spacing is also D. These are connected by a duct configured LAN as shown in the figure, which means that there is a duct that connects every station to every other station, which means there is a there is a duct as in a cable container, right? Ducts would actually mean that it's a pathway that is possible, but there's no fiber yet. Okay, there's a pathway that is possible. Given that M is equal to 7 and N is equal to 11 and D is 2 kilometers. So this is like kind of a grid of computers in a particular, an institute or in some kind of establishment. The question is, what is the minimum? So the first question, sorry, let me pick up the question correctly. This is question 4. Question 5. What is the length of the cable required to connect it in a bus configuration? So how do you make a bus configuration now? You would say that, let me try to make the connection this way. And so on. So what is how do you now connect this cable now? What is the total length of the cable that is required? So it's now very easy. Now you have N rows, and how many connections you need to make in each row. So each row has M computers, so you need to make M-1 connections, M-1 stations per row. So that is the row that you finished counting, this one plus this one plus this one plus this one plus etc. And you should also be making these interconnections between the rows, right? It's not just enough to connect these horizontally. You need to make them, you need to connect them, the interconnects. And how many interconnects you need to make? Because there are N rows, you need to make N-1 interconnects between rows, right? And each connection, these are the number of connections. Each connection is of a length D. So you can calculate what is the total length. So that is when you are trying to connect. So you would have, let me just take the example of, just complete this grid. I would connect this way. I have given, for this purpose of demonstration, I've taken M is equal to 5 and N is equal to 4. But then this is for any M and any N. This is how you would actually make a bus connection. Okay? The next one is how do you now convert it into ring configuration? So you have to remember one fact, that you cannot think of anything other than using the ducts that are connected in between. There are certain ducts that are available, so you have to use the duct. So you cannot arbitrarily design your ring. You have to now think how to use this duct to connect to the ring. So how does one do that? So that is something that I'm not going to reveal. You can check. It is actually a very minor modification. How do you now connect? So you already made this connection, and in ring you want something you have thought about this configuration like this, right? Where so how do you identify? You started from a point, you go all the way around. So you started from this point, you go all the way around, you reached here, and then if you want to make it as a ring, you just need to make one connection. So I'm not revealing the answer. You can think and find out what is that one connection and what is the length of that one connection you need to make, and then find out the answer. Now the next one is if you want to convert this into star configuration. So in a star configuration, what do you do? So you say that, okay, let's take a simple case, 1, 2, 3, 4, and this kind of bus. Again, an example. In star, hub is at the one corner. So let's say this is the hub. And what is a peculiarity of the star? This hub gets connected to every other point. So you cannot think of connecting this way because the duct is not available here. So don't use any general formula for star and say that that general formula I used to calculate and that's not working here. It won't work here because general formula assumes that you can find the shortest distance. Whereas you have to remember that in this particular problem, you can use only the ducts that are connected in between. So all what you need to find out is that, for example, how do you connect to this point from this hub to, let's say, the point that I'm marking in black? How do you connect? So you cannot do this diagonal connection. You have to do it maybe from here to here, or you have to maybe do from here to here, right? That's how you will establish this star connection. So the cable runs from hub to each station. So the total length of the cable in this case. So essentially, you will need to run a certain number of cables along the vertical and a certain number of cables along the horizontal, right? So certain number of cables need to be run along the vertical and certain number of cables need to be run along the horizontal. This becomes more like a number theory problem now as to what is the minimum number of cables, for example, that you need to run to connect from each hub to this point. And it's not actually complicated. So I can tell you in one way of doing this. So you can say that it is, so you have M is the number. So this is M and this is your N. Okay. So start from one corner. And I think the best way for you to do this is to pick some certain values of M and N, maybe 4 by 3, and write it for that case. Maybe you should pick for 2 cases. This is the smallest unit. Write down what is the number of cables required. So you need to go 1 step here, you need to go 1 step here, and you may need to go 1 step here, right? So the total number of cables in this case is actually 3D. Similarly, now you try to extend it and check how many steps you need to go to get it to extend it by 1 more row, then extend it by 1 more column. Then you try to generalize your formula. Now, I'm not going to explain the details, but it will come out to be M times, because there are, M vertical columns. So M times summation I is equal to 1 to N minus 1, because you need to make only N minus 1 connections, I times D. So this comes in because you try to keep connecting one to the next to the next. So you can write it as a general formula like this. Plus, similarly, you need to, so this is for M times, and then you will do it for N times for the N rows. So this will be N times summation I is equal to 1 to N minus 1. Sorry, it should be M minus 1, because again, ID. So think through and work out. There is no physics here. It's only just trying to find the numbers. Then you can actually redo this for the next question where the position is m is equal to 3 and n is equal to 2. So there you want to now say that now your L becomes n times I is equal to uh, 1 to n minus, m times I is equal to 1 to n minus 1 ID plus m times I is equal to 1 to n minus n ID, where your m and n is given here. Because the reason being that if your hub is moved to the center, the number of connections that you're saying that so you can start by considering that instead of the hub being here, think about what happens when the hub is here at this point. Then you will realize how many connections fewer you need to make, right? And so this we did for the m, and similarly we need to do for the n. So we need to say that this is n times I equal to 1 to m minus 1 id plus n times I is equal to 1 to m minus m id. Think through. It's a question of trying to figure out what is a generalized formula. Again, as you said, do not use a general formula that could be derived in some textbooks for star networks and so on, because that is assuming that you're able to make the shortest distance connections. The next question is, what is the value of m and n such that it gives the smallest length? Now, these are infinite sums, so you can use the formula for infinite sum to reduce this answer to smaller. For example, you know that sum of 1 to n minus 1, you know how to calculate that finite sum. Now, it's not really infinite sum, this is finite sum. So you should be actually writing the expressions for these finite sums. And then you want to minimize the length. So you want to minimize the length. So you basically differentiate with respect to dl with respect to dm or derivative dou L by dou m you can calculate, and dou L by dou n at a given for an m you can calculate, and then you can equate to 0, and that will give you the optimal value of, so you can do this, and that will give you the optimal value of m and n. So for that you need to have done the finite sum formula. You need to have done the finite sum of these terms to be able to do this differential. The last question, okay, the last two questions are actually simple enough. There is a measurement on a n by n star coupler. It gives an insertion loss from port 1 to each of the output ports. So essentially, this is question number, what's the question number now? Question number 10. So it's an n by n coupler. So you have n input ports and you have n output ports. And if you give power from 1, what are the insertion losses is given? Find out the total excess loss. Now, if it is an regular loss, the coupler loss, we saw that it is minus 10 log 1 by n. This is the regular coupler loss. But in addition, there is some loss because of the irregularity or the non-ideality in fabrication, and that is what is giving rise to this excess loss. So essentially, what it says is that insertion loss is what is given. So what is given is if I if I give input port in 1, between port 1 and port 1, if I measure, the loss is 9.33 dB. Here in port 2, I measure 7.93 dB. which means this port 1 is more lossy. It has more excess loss than port 2, obviously. Port 3 is 7.53 dB. It's slightly even better port. Like that, you are all the way going up to n is equal to 7, which is 9.04 dB. So so for a n by 7 coupler, 1 by 7 coupler, you know what is this splitter loss. So which means that you can calculate what is the excess loss for each port, right? Now the question is, what is the net excess loss in this? So the net excess loss, how do you calculate? It will be 10 log input power, I mean minus 10 log you can put in, input power divided by summation of all the output powers, where I runs from 1 to 7. Now, but we don't know the output powers, we know what is the insertion loss. So I can write it as minus 10 log P in divided by insertion loss. How do you calculate the insertion loss of each port? Each port insertion loss is P in divided by P out. So, I mean, to input power divided by the output power. Again, negative should be there. So, which means that P out, I don't know P out. So that P out is actually equal to P in divided by insertion loss. And you can do this for each port, right? So now, so okay, there's no P in of I, the P in is constant. Okay, so in each of these terms, I can take out the P in. So I can say that this is P in divided by P in times summation of 1 over insertion loss I. So this cancels. I know what is the insertion loss in each. Now I can calculate what is the excess loss. So I hope that's clear. And the last question is, a cable TV operator uses an optical bus. So he uses, there is a transmitter, and then there is a tap coupler. Then there is a tap coupler. Tap coupler means coupler where the split ratio is such that what comes out, you're taking out is much smaller than what is in the feed through path. So this is user 1. So you can think of what topology is this. User 2, etc. Now this is a configuration. This is a configuration that is used to just drop. There's no uplink here. There's just kind of downlink. You keep multicasting. Now, after each user, the power reduces. So the last tab is user N. The question is, the receiver needs minimum of 100 nanowatt. This receiver needs 100 nanowatt to operate satisfactorily. The couplers couple a power ratio. So as I said, this power that's coupled out is small. This is 5%. So this is 95%. Assuming 0.5 dB insertion loss for each coupler. So this is insertion loss, which means this includes the splits loss and the excess loss. So 0.5 dB at each coupler. Find the number of and 1 milliwatt of transmitted power. So this is also given. So you have all the information to calculate. You need to generalize. You need to find out the loss of nth coupler as a general formula, and then you can find out what is the loss. Loss at I mean, if you can write down the loss, or rather, we can write down what is the power received by the nth nth user, right? And as you have recognized, as I told you, this is a bus topology. Okay, so let's say to start with, instead of taking 1 milliwatt, let's say X is the power here. Now 5% port gives you how much power? 0.5. So first of all, 0.5 dB will correspond to a ratio of, I think, 0.89. Work this out as a power ratio. So what will be the power here? So the power here will be, okay, let's just do it for the nth user. Let's do it for the first user. Then you can extend it for the nth user. Okay. 0.89 is the insertion loss. So 0.89 into x is what comes out. Of that, so user 1 receives. Of that, you're getting 5% only. So this is 0.05. Okay. User 2, how much, what does he receive? He has 0.89 square because it goes through 2 times the 2 tap couplers times it is also crossed. He is also receiving only 0.95%. So which means he receives 0.95 times of that. And he receives only, so 0.95 times 0.89 square is 0.95 times 0.89 is what reaches at this point. And of that, he experiences a loss and he is receiving only 0.05 times the x. Similarly, so you can write what is the nth user, what does he receive? It will be 0.89 n couplers, 0.95 n minus 1 couplers, because he would have suffered loss from n minus 1 couplers because he is getting only 95%, 0.05, that remains the same, x, and you want this to be 100 milliwatt. You know the x actually. So you can now calculate what is the value of it. You have to do something slightly smart here. I never said that this is 5% or this is 95%. I can put the user here to get the largest benefit. So in the last user, you have to assume that the last user gets 95% and not 5%. So that change you need to do. So we are done with the assignment questions now. So if there are any other questions, please type in. Before the exam, we can have one more session. You can, if you need that session, you can reply in the course forum. We can have the session maybe a day or 2 days before the exam so that you would have revised everything. And then we can have an interaction on, your questions regarding the course. So maybe a couple of days before your exam date, we can have this one more interaction session. In the meantime, you're also free to post your questions in the discussion forum. We'll keep it open and you can, and we'll try to clarify the difficulties as soon as they come in. Are there any questions? So question 2 is just says, if everything is identical, what is the upstream data rate compared to the downstream data rate? Answer is very simple. The upstream data rate, if the transmitter, receiver, everything is the same and the sensitivity is the same, then it just means that in the upstream, I can transmit, each of the venues can transmit as much as the downstream. And the downstream, which is from OLT to ONU, let's say you have a bandwidth B, that gets divided by N among the N users. But each of these guys can actually transmit B because they have the same transmitter receiver as that of the OLT. So that is why I say upstream is upstream data rate can be in principle larger than the N times larger than the downstream data rate. Any other questions? If not, we will close the session, but keep your questions up in the discussion forum.